So good morning, everyone. Welcome back to ECE 2002. I hope everyone started studying for the exam. First thing is, just like last time, I will plan to hold office hours between Sophie and Pranav's office hours tomorrow. So that way I can be a little bit instrumental in bridging the gap between, okay, we have, some office hours basically all Wednesday to make sure people have a chance to get things answered leading up to the exam. I'll make a note on Piazza about it. Exam 2, you should have all the practice exams and everything else you need. My goal is basically finish all of lecture set 6 and then use the remaining time to answer and work out any problems of your choosing. So if you do have problems that you want to see me work out on, the second half of Wednesday and on Thursday, do message on Piazza or something like that, preferably on Piazza, but I guess you could email me just so I have record of what sort of problems people want to see. Right now, I think I have a regular algebraic convolution problem, a graphical convolution problem, a transfer function to do inverse Laplace transform and Bode plots with, and then like 3 RLC circuits, just to work out and demonstrate various things. Are you going to be able to finish the exam? Well, I can't make any promises. That really depends on you. There were people who finished exam 1, and I was, shocked that there were people that managed to finish exam 1 early. I think more people will finish exam 2. That being said, I don't think the majority of people are going to finish exam 2 in time, just because this is complicated material. I do want everyone to get further along on exam 2 than they did on exam 1. So again, my goal is to have the mean 60 or above. So we're tailoring the difficulty and the length of the calculations to make that possible. Yeah, I mean, I really want a much more pleasant experience for exam 2. I think some people got demoralized after exam 1, and I want to leave people feeling a little bit more confident. Though I think when the final grades were released, I think most people were fairly relieved. That being said, I think that does it for my announcements. We are wrapping up this course faster than I am ready, especially when it comes to grading. I am ready for the lecture materials, but I'm not ready in terms of grading a total of 4 more assignments and 2 more exams. That scares me. So I'll give the class an option. I think I have an idea of where things will go. Do you want to go over the new slides I added about frequency response in lecture set 5 right now, or do it later after we talk about the stuff that's on the final exam with lecture set 6? So do you want to do lecture set 5, the new stuff, or do you want to do a continuation of lecture set 6? Vote now. Well, I think that's unanimous from the sample of votes we have now. Let's go ahead and do lecture set 5. Luke, that's a nice try to get out of homework. So many people, I think, really think the homework is good. That's credit to our TA, Sophie, who works very hard to make sure the assignments give you a chance to explore the topics better than I can teach them just with pure lectures. Go, Sophie, indeed. So I don't think you would want just exams, no homework. Yeah, that's a weird sound I just heard. Yeah, shout outs to Sophie, indeed. Snap, snap, snap. Okay, let's do lecture set 5. So lecture set 5, frequency response. I didn't change anything with the complex poles and stability. I didn't change much with resonance and second order systems, except I did fix on the parallel RLC side. I finally fixed this so that the minus sign is in the right place, and this is talking about Y in. So that's good. Frequency response, I made quite a bit of changes to the Bode plot section. Magnitude and frequency scaling, everything looked good there. Bandpass response, second order systems, I corrected some typos, but for the most part, it was good. And I added something about the band stop. So let's just jump right back to frequency response, do a little bit of refresher. So again, we care about the frequency response because most signals in real life are made up of multiple frequencies, whether that's an instrument, my voice, something coming out of a sensor. There's going to be multiple frequencies involved. So we don't want to know just what happens at a single frequency like we do with phasers typically, but we want to deal with multiple frequencies. So if we do the polar form with magnitude and phase, we basically get a frequency response because we can plot them separately with logarithmic frequencies axes. So frequency response must contain the magnitude response and the phase response. And then we only evaluate with S equals J omega, which is basically saying we're sticking to the imaginary axis. So only inputs and outputs that are, sinusoids or steps. So we did this algebraic example with a series RC circuit. Okay, where we convert the circuit into impedances. So R and 1 over SC. We did voltage division, 1 over SC over R plus 1 over SC. This is where everyone has to be really good with what they learned in ECE 20001. You have to be able to, know the voltage divider formula and the current divider formula without hesitation. Like, if you hesitate, you're going to have a bad time on this exam. Similarly, source transformations. As you learn, hopefully some of you noticed for problem 1 on homework 5, there's just a bunch of resistors next to the voltage source. You could just repeatedly do source transformations and combine parallel and series resistances in order to reduce it to a series RC circuit or a parallel RC circuit if you so chose. But regardless, a single R and a single C in problem 1 of homework 5. So that's where knowing how to do ECE 20001 stuff and being able to spot it could save you a lot of effort than having to deal with complex algebra with transfer functions. So anyway, we have our transfer function in S world. Let's move it into J omega, phasor-ish realm. I guess not single frequency phasor, but frequency response realm, I should say. So we'll get 1 over 1 plus J omega RC. The magnitude response, well, how do we take the magnitude of complex numbers? So recall the quotient of complex numbers, Z over W is just the magnitude of Z over the magnitude of W. So we'll get magnitude of 1, it's just 1, over the magnitude of 1 plus J omega RC. Remember, it's the square root of the real part squared plus the imaginary part squared. So square root of 1 squared is 1, plus the square root of the imaginary part. Remember, we leave out the J, and everything after it is the imaginary part, omega RC, or in this case, RC omega quantity squared. And then we need to do the phase response. So remember, the phase of quotient of complex numbers, Z and W, is the phase of Z minus the phase of W. So the angle presented by a real number 1 is just 0 because it's a positive real number. If it was a negative real number, it would be 180 degrees. If we have this number in the denominator, remember the phase of this, complex number in the denominator is just going to be arctan of the imaginary part, which is just omega RC, over the real part, which is just 1. So arctan of RC omega. We take 0, we subtract arctan of RC omega, and we get just negative arctan of RC omega. So that's the review over, how we calculate the magnitude and angle of a complex number and how we do that with, the division of complex numbers. And then we plot the responsive logarithmic frequency axes from 1/1000th of a radian per second to 10 radians per second. And we got something that looks like this. And we made a bunch of observations, as what happens as omega goes to 0 in magnitude and phase. We saw here, there's the greatest drop here. We saw here, immediately after our, cutoff frequency. And then for the 2 decades centered on the cutoff frequency, in other words, from the decade before the cutoff frequency to the decade after the cutoff frequency, that's when you had the most phase change. And of course, as omega gets very large, we said that the magnitude response goes to 0 asymptotically and goes to negative 90 degrees in phase. So, this looks like a capacitor because, it's, phase is 0, and then way over here, it looks like looks like a resistor way over here for low frequency, and a high frequency looks just like a capacitor. So now we're going to talk about the decibel approximation for a series RC circuit. So I claimed that it was a straight line with a negative 20 dB per decade slope. So if we look at the decibel of version of the magnitude response, 20 log 10 of h to j omega for this RC circuit, it's going to be 20 log of 1 minus 20 log of square root of 1 plus RC omega quantity squared. 20 log of 1, well, log of 1 is 0, regardless of the base. And, we're dealing with the common log, so I dropped the subscript 10. So we have square root of something is the same thing as the argument to the 1/2 power by logarithm properties. Logarithm of a number to a power is equal to that power out front times the logarithm of the remaining stuff. So that's how we get minus 10 this. Now here's where we do a big approximation. We say RC omega quantity squared is much, much greater than 1. And it will be for most cases except near the cutoff frequency. So what we're going to do is just say, okay, it's equal to RC omega squared alone. Well, we have another log of something. So we'll just say it's minus 20 log of omega. And then we'll have plus k, where k is going to be plus, minus 20 log of RC, where minus 20 log of RC is just a constant. We'll call it k. So this looks like a straight line. So it's, negative 20 dB per decade slope. Log is just our independent variable, logarithmic frequency. And then k is just a constant, so our vertical shift, y equals mx plus b, is going on right here. And, this is the result of this approximation, which is good for, omega much greater than the pole frequency being considered. So at the pole frequency, omega p is equal to 1 over RC. We'll get 20 log base 10 of 1 over, you put in these numbers and you'll get 1 over square root of 1 plus 1 squared. Something is saying 20 log 10 of 1 over square root of 2. And if you work that out, it's negative 3.0103 decibels. So that's where we get, that number, 3 dB down, 3 decibels down is same thing as, saying the magnitude response is reduced by a factor of 1 over square root of 2. At the pole frequency, we'll get, negative arctan of, omega is just equal to 1 over RC, so negative arctan of 1. But arctan of 1 is just 45 degrees. It's where sine and cosine have the angle at which sine and cosine take equivalent values. So we'll just say negative 45 degrees here is what's happening. So sure enough, at this pole frequency of 1/10 of a radian per second, we're at 1 over square root of 2, and we're at negative 45 degrees. So that's exact values when we're trying to get things straightened out. Graphical approach, nothing changed here. Definitely a curious way to do it. I never really thought about this until I read your textbook, but It is an interesting way to do the frequency response. But the Bode plot is definitely the more important technique to learn. So it's inefficient to get exact magnitude and phase response when you have many elements. So we're going to capture the major behavior based only on pole and zero locations. We're going to sacrifice a little accuracy to get a piecewise linear approximation through Bode plots. And it's a log plot for the magnitude response because we're using decibels. And then remember, we're talking about complex frequencies. So it's the distance to the pole or the zero from the origin. So in the complex world, we have, the pole is located, vectorially at, some magnitude, which is the complex frequency, and some angle, which is just, the pole or zero angle. The angle not being that important, except when we're doing the graphical method. But the complex frequency is. We talked about the rules for poles. So for every pole in the left half plane with distance from the origin omega p, magnitude of plot changes to 20, an additional minus 20 dB per decade down, beginning at the critical frequency omega p. And the phase plot decreases by 90 degrees starting a decade before, ending a decade afterwards at that critical frequency. And if we have a right half plane pole that's, instability, it would instead cause an increase in phase. The magnitude at the critical frequency itself is 3 dB down from the asymptotic expectation. Hence, that's why we did this calculation with what happens exactly at the pole frequency. It shows us the error in our approximation. And of course, exactly at the pole frequency, we're at negative 45. We're, 45 degrees down from our initial phase. And every pole and zero passed is cumulative at a given omega p. And for a zero in the left-hand plane with distance from the origin omega z, magnitude plot changes asymptotic slope to plus 20 dB per decade up, beginning at the critical frequency. Phase plot will increase starting 1 decade before, ending a decade afterwards, by additional 90 degrees. But if you have an unstable pole, it'll instead cause a 90-degree decrease. Just keep that in mind. And then the actual magnitude is going to be 3 dB up from asymptotic expectation for real poles. I should say zeros. I found an error. And I don't have my notes out. I can't believe it. I found an error. I've worked so hard on this. And again, every pole and zero is cumulative. And perhaps the most requested slide is this slide right here. C019, I forget who is that. It's Aubrey. Yep. It's actually on slide 31. So I will answer your question about slide 23 on slide 31. So the process for drawing Bode plots. So here we go, the most requested slide. Some of you wish you had this sooner. I can only work so fast though. I'm just glad I got it out before your homework was due, so at least some of you had a chance to figure things out for question 6 on homework 5. Anyway, so what you're going to do is identify all the poles and zeros of the transfer function. So that's where we go back into looking at the factored form of a transfer function. Identify all the poles and zeros. Label the critical frequency associated with poles and zeros. So remember, we're going to think in complex frequency. So that's distance from the origin, not in terms of like, being a real pole on the negative axis or having poles that are, have a real and imaginary component. We'll just think in terms of their complex frequency, and distance from the origin. Draw your matching logarithmic frequency axes, log base 10 of omega for the magnitude response plot and the phase response plot. You should include all non-zero finite poles and zeros in the middle. So obviously you can't graph a pole exactly at 0, but if you have a pole at, 1/1000th of a radian per second, make sure that you have 1/1000th of a radian per second in your plot. Ideally, you would plot from 1 decade before, and then say your highest one is at 100 radians per second. Should it plot at least up to 1,000 radians per second, if that's your highest zero per se, per chance, I should say. Consider what happens as omega goes to 0 for both plots. And then we'll find the vertical position of the magnitude response plot using a test value if needed. And apply pole and zero rules for each one in turn, counting multiplicity. And we'll consider what happens as omega goes to infinity for both plots. So, basically after we have our frequency axis drawn, we'll figure out what happens as omega goes to 0. We'll position the magnitude response vertically. Shouldn't need to do that for the phase response. Consider the pole and zero rules for each one in turn. So we apply each of those rules on the previous 2 slides. And we figure out what happens as omega goes to infinity. And then step 8, optionally, you improve your sketch by including the curvature above or below asymptotes and verify with a computer algebra system. So here we go. Step 1, identify the poles for this transfer function, which is the exact same one was shown on slide 23 with the series RC circuit. It's 1/1 plus SRC. There's no zeros here, and one pole at S equals -1 over RC. The critical frequency is at omega p equals 10 radians per second because this is the value of RC. So we did, step 1, and then we've got step 2. We figured out what that critical frequency is. Frequency axes should be between 10 to the -1 radian per second and 10 to the 3rd radian per second. I decided to go 2 orders of magnitude out from the pole frequency. If you were really lazy, you could probably get by with just more than 1. But, I would recommend that you do more than 1. So step 4, we consider what happens as omega goes to 0. Well, h of J0, plug in 0, J0 for S here, you get 1/1, which says the magnitude is just 1, or that it's going to be 0 decibels. So we know that the far left hand of the graph is going to start at 0, and it's going to have a flat slope because there's no polar 0 at 0. And the phase plot starts at 0 degrees. Why? Because nothing has made it change from being 0 degrees. There's nothing, so 0 degrees is the only option. H of S is 1/1, so that's a purely real number. Purely real numbers have 0 degree phase. So basically, we don't need a test value because there's no pole exactly at 0 or no 0 at 0. So we just use these values to vertically position our magnitude response, like I said, so we know it starts along 0 dB. Where here you can see my labeled axis, where this is magnitude of h of j omega, and this is angle of h of j omega. The Bode plot rules for the pole. Once we reach the pole, we slope downwards at 20 dB per decade. Once we reach 10 to the 0th radians per second, we start sloping down at -45 dB or -45 degrees per decade. And then we end that slope exactly at 10 to the 2nd radians per second, where then it'll just flatten back out again. After you do all your phase response, it'll just stick to its value after that. So what happens as omega goes to infinity? Let's just check our behavior. We could be done here, but we want to make sure that we didn't screw up. So h of j omega goes to 0, which is the same thing as h of j omega goes to -infinity decibels. Yeah, this line will just continue forever. It's going to end with its minus 20 dB per decade slope after all pole 0 interactions. Yep, ends at that slope. Has to be a negative slope to go to -infinity. And then angle of h of j omega ends at -90 degrees, because if you plug in, the angle into here, let this get large, we'll get negative arctan of infinity, which arctan approaches pi/2 radians as it goes to infinity, which is the same thing as saying negative arctan approaches -90 degrees. Aubrey, does that answer your question? I think that does it. MATLAB is definitely good for checking your work. You won't have MATLAB on the exam. That would be cheating. Don't open MATLAB or Mathematica or anything else on the exam. That's bad. No internet connection allowed. Wow. No internet connected calculators. If there were two poles at 10 radians per second, would the phase response go down 90 degrees per decade? Yes. Basically, we would apply this rule for poles twice. So it's instead of decreasing 90 degrees over 2 decades, it would decrease 180 degrees over 2 decades instead, which is the same thing as saying negative 90 degrees per decade slope. So instead, it would drop down through negative 90 at 10 to the first radian per second and end at negative 180 radians per second. And you can also see here, I've included the exact responses. We can do that. We just go 3 dB down from at 10 to the first, and we just smoothly connect the asymptotes through that point we would draw, clinging very closely to them. And then drawing the phase response exactly is a little bit hard. You kind of have to be comfortable with how arctan twists and turns, but you can see arctan will just kind of overshoot a little bit, then it'll undershoot and level out. You're welcome.
Could you go over the points where you said if it's a complex number, the actual point will be 3 decibels lower than the Bode lines.
Right. So regardless of whether it's a complex, pole or zero, you will get that. You will get that the actual exact magnitude response is 3 decibels lower for a pole. Now, if it's a complex pole, it's going to be a resonant peak that goes above. So say, for example, we had poles that were, this is going to be very tricky. Let's do a 5, 12, 13 triangle. So we'll say that it's negative 5 nepers per second plus J12 radians per second. So we'll have negative 5 plus J12 and negative 5 minus J12 as our pole. Both of those poles are located at a distance of 13 away from the origin. So it's the same thing as having a critical frequency of 13 radians per second twice. So that means we have to basically apply the pole rules twice at what's happening there. So what's going to happen is instead of this sloping down at negative 20 dB per decade, it would slope down at negative 40 dB per decade. And instead of going below, according to our note bene, we're gonna have a complex pole produce a resonant peak above the asymptotes. So the exact response, instead of going 3 dB down, would be okay. It stays flat, and then it bumps up, and then it dips back down and clings to the asymptote. Let me see if I can possibly graph that for you, Salem. Grapher. Open grapher. Okay. Probably wanted linear log. Lay out axes and grids. Cartesian, polar. We'll just start again. Open grapher. I want lin log. No, I want log. Sure, we'll do log. We'll just be off by a factor of 20 on the vertical axis. Okay, so let's plot this. So 20 log. of what we're going to type. So what we're going to type is 1 is 1 divided by square root of the magnitude of that pole as well, 5 squared plus 12 squared. And we're going to have another one of those. So we just square the square root. Oh, that's just a point. I'm really struggling. Let me get back to you. I don't think this is the best use of class time. I will try to just prepare what I have. Remind me, let's see, make example with complex poles. I'll do that. Just complex poles. I have an app called Alfred installed. Alfred is great. It's basically like Spotlight, but better. Instead of having, for those who want Mac tricks, instead of command space to open Spotlight on a Mac, it's shift command space for me to open Alfred. Definitely worth the trick if you're a Mac user. Basically, it's like having a little terminal to open props, apps whenever you want. Okay. I'll get back to you, Salem, with just complex poles. So sketch the Bode plot for the given transfer function. 10 times s over s plus 1, s plus 1/100th over s plus 10 quantity squared. So we do the exact same trick. We identify the poles and zeros. So there's zeros as s goes to 0, s equals -1. Poles at -1/100 and -10 of multiplicity 2. So we order them and call them our critical frequencies. Excuse me. 0, 0.01 radians per second, 1 radian per second, and 10 radians per second, multiplicity 2. We'll draw our axes, so logarithmic axes. Basically we can't include 0, so we'll just do from 1/1000th of a radian per second, or actually 1/10,000th of a radian per second, all the way up to 2 beyond that, so 1,000 radians per second. Figure out what happens as omega goes to 0. We'll get negative infinity decibels because we're starting with a 0. So we'll have to start with a 20 dB per decade slope, and we have to start as though the 0 were fully resolved. So at the end of resolving a 0, you'll start at 90 degrees. However, we still don't know where, we know what slope we start off, but we don't know how to position it. The only way I could think of to do it, to find the vertical positioning, is to use a test value. So you just say, okay, in this, we're going to plug in everywhere we see S, we'll plug in J, 10 to the -3rd radians per second. So we'll just use the value at 10 to the -3rd radians per second to figure out how high up or down the slope needs to be. So you'll do that and you'll get that, it's roughly -40 decibels. So with that, we can apply the pole 0 rules in turn. So we have our next pole at 0.1 radians per second. So then we decrease the slope on the magnitude response, and starting at 10 to the -3rd, we'll do a slope downward of -45 dB per decade, degrees per decade rather. Then we have at 0 at 1 radian per second. So we'll increase slope by 20 dB per decade immediately afterwards. And then starting at 10 to the -1st radians per second, going up to 10 to the 1st, we'll say there's a cumulative plus 45 degree per decade slope. Then we have a pole at 10 radians per second, multiplicity 2. So we go from plus 20 dB per decade slope to 0 down to -20 dB per decade slope. And then that will continue up until infinity, as we will check right here. and we will have h to j omega, end at negative 90 degrees. How do I know that the slope is like this? Well, the order of the denominator is 1 greater than that of the numerator. So the transfer function gives away what happens at infinity. And because of this, we also expect ending at negative 90 degree slope. So we didn't talk about the phase response. So because of here, we're going to get, we add a minus 90 degree per decade slope starting right here. And it'll end at 10 to the negative 2 or 10 to the second radians per second. All these effects are cumulative, so we get, the Bode plot shown in red. And if we want to plot it exactly, well, we have to do all of our approximation rules to find the points 3 dB down, 3 dB up, 6 dB down for the double pole, connect it with smooth curves. And then exactly phase response is kind of a nightmare. The Bode response is much better. Does that answer any questions? Is this better than what it was before? People feel like they understand things a little bit better. Yeah, good. I'm glad. Hopefully you're prepared for a Bode plot on the exam. In addition to plotting out time domain waveforms, we can ask you to do a pole zero plot. We can ask you to do Bode plots. We can ask you to plot the transfer function in any number of ways. But you can see now I have the exact phase response, which was missing in the original presentation of these slides. So that allowed me to correct an error where I had the wrong Bode plot before. As you can see, it oscillates around these asymptotes pretty wildly because, some of these poles and zeros are separated by only 1 decade. So you're off a little bit, but you get the right overall idea of what's happening. So basically you go from acting like an inductor to acting, mostly like a resistor, but somewhat like an inductor, halfway in between a resistor and inductor, just like a resistor, and then finally like a capacitor. If this was like an impedance interpretation of what's going on here. Okay. Because hj omega goes to 0 when omega is 0, phase response starts at 90 degrees. Yes, because of our zero rules, we basically say, okay, we can't say, it happens over 2 decades centered at 0 because you can't have things less than 0. So basically you say it just has to start at 90 degrees because it's like this, this zero rule has already resolved itself. You have to take a test point on every Bode plot to find the exact line. For the simple Bode plot here, our test point was just figuring out what happens as omega goes to 0. So sometimes you don't need an additional test point, but there's always at least one point you have to test. Yeah, I'll be holding office hours remotely today. Unless someone wants to meet up in person, I will be holding my normal office hours today. Everything we learned about magnitude and frequency scaling, basically unchanged. What I did want to go back over was, for some of you that missed it, was bandpass responses. So here, basically we figured out that for this parallel RLC circuit, because of resonance, L and C will appear as though they were an open circuit at the resonant frequency. So the emittance will reach its minimum value of 1 over RP at that point. So if you look at the impedance response, so 1 over the admittance, you'll get that, we reach a maximum value of RP at omega equals equal to omega R. Or that's, in this case, since they're all in parallel, they're all equal to the natural frequency, which is 1 over square root LPCP. And remember, we also had the attenuation sigma p defined as 1 over 2 R sub p C sub p. We called this a bandpass characteristic. There's a certain band of frequencies transmitted by the circuit without significant attenuation. There's a 0 at the origin and at infinity. So basically for really low frequencies and really high frequencies, you basically get, 0 in your transfer function. And then in between, the effects of the two poles are felt. So you can plot this out. We can say at omega sub m, the center frequency, the frequencies at which you reach maximum of your transfer function, center frequency. We have the maximum itself, h sub m, and then over at h sub m over square root of 2, we have omega L and omega H, the lower and upper cutoff frequencies. Then we defined, or we notice also that at h sub m, or at omega sub m, I should say, where we have h sub m, we also have 0 degrees. And at omega sub L and omega sub H, we're at plus 45 degrees and minus 45 degrees. So we define new quantities, the bandwidth, specifically called the half-power bandwidth, omega H minus omega L, and the quality factor of the bandpass characteristic defined to be omega M over our bandwidth. So the bandwidth measures how wide this pass band is in absolute terms. And then the quality factor measures how sharp the central peak looks, basically regardless of where it's located in frequency. So rule of thumb, Q greater than 10 is a high Q system, and it has a narrow peak. A low Q system would have a broad peak. We derived with some effort, expressions for the upper cutoff frequency and the lower cutoff frequency, and we noted that the bandwidth is just going to be 2 sigma p. Q is just going to be R sub p over square root of LP over CP, written in this way because it's suggestive of things you're going to learn in lecture set 8. And then we'll have omega naught over 2 square root of p, or 2 sigma p being equal to Q. If we have a high Q system, we can just approximate the upper and lower cutoff frequencies using the center frequency and the bandwidth. Otherwise, regardless of how high our Q is, this geometric mean interpretation holds. And we can rewrite a transfer function one of 2 ways, 1 over Cp times S over S squared plus 2 sigma PS plus omega naught squared, or the same numerator, S over S squared plus bandwidth S plus center frequency squared. Higher the Q factor is considered better in the sense that it behaves closer to an undamped system, as though there were no resistance involved. So that means you get a very sharp peak, which is sometimes what you want. That means you're, band passing really well. Only a very narrow range of frequencies get through this this circuit. Bandpass filter. The bandpass expression, it's not always 1 over RPCP, but being equal to twice the attenuation holds true for every second order circuit made of L's and C's, R's and L's and C's. Holds true for every circuit made of just 1 L and 1 C, I should say. Why sometimes what you want? I mean, say for example, you're picking up a lot of noise at 60 hertz because of, that's power line frequency. And you're also getting a lot of, radio noise up at, I don't know, maybe not radio noise, but let's say you're next to something that emits a lot of noise at, 100,000 hertz or something like that. You would want a bandpass configuration in order to get through only the stuff in the middle while leaving out power line noise and that noise at 100 kilohertz. And, the sharper it is, the more selective you can be. So if it's a high Q system, basically, I can not just separate noise, say my target is 8,000 hertz. I can now start separating noise that's not just, at 1,000 hertz and 15,000 hertz. If it's a high Q system, I can separate noise that's at 6,000 hertz and 10,000 hertz. All right, this is something I want everyone to pay close attention to. What makes this a bandpass characteristic is that we have a zero, a zero, single zero. So it's just an S right here over a quadratic polynomial. So, I mean, there are other ways to do it, but the fact that, there's a zero at zero and off at infinity because the order of the numerator is less than that of the denominator makes this a bandpass circuit. We know it has to be zero at zero, zero at infinity. So that means it has to be non-zero in magnitude in between, because these are interesting non-zero values. So we looked at, this is a moderate Q system, and we noticed that for a low Q system, it looks still underdamped, but it looks like this. And then critically damped, quality factor drops to 1/2. It doesn't really make sense to talk about bandwidth past that point. It's just kind of weird. Q below 1, it doesn't make too much sense to talk about bandwidth, but that's besides the point. The series RLC circuit works very similarly. Remember, omega R is omega naught 1 over square root LSCS for the series inductor capacitor. And then sigma P is RS over 2 L sub S. The admittance has a very similar transfer function, bandpass characteristic, where again, the transfer function for Y in of S is going to be 1 over LS times S over S squared plus bandwidth times S plus center frequency squared. Where now we just have, bandwidth still equal to twice the attenuation, RS over L sub S. Our formulas for omega L and omega H stay the same. And then Q is now 1 over RS times square root of LS over C sub S. Or again, the square root of L over C is something that's reminiscent of what we'll see later on. Or regardless, omega M over 2 sigma P is fairly standard for all circuits. And we talked about how frequency scaling works, and then the band stop response. So your book completely omits the band stop response, but it's a completely different type of filter. So it's also called the band reject characteristic or the notch filter characteristic. So for the circuit on the left, basically we have R sub P over times quantity S squared plus omega M squared over S squared plus B sub omega S plus omega sub M squared. So notice the denominator matches what we're used to. So I guess this one is like the series LC circuit, RLC circuit. We have bandwidth right there. We have natural frequency. It looks very similar to the series RLC circuit. This right circuit looks like the parallel RLC circuit. So we have these expressions coming into play right here. So we'll say 1 over our, RSCP shows up. So we get the same denominator form, but 1 over RS S squared plus omega M squared in the numerator. What makes this a band stop characteristic? There's 2 zeros, both located at omega M. Far from the zeros, the effects of the 2 poles are felt, so you get a non-zero response. And then, I basically said, it's like the series when calculating, sigma P, omega L, omega H, B sub omega, and Q. We don't focus too much on them. The book thinks, well, if you figured out one, you figured out the other. And we always talk about band pass and we never talk about band stop. But I thought that was kind of wrong. I would at least lay out what it looks like. So if I ever show you, okay, here's a transfer function where we have 2 zeros at the same location in the numerator. And then we have a quadratic, with complex roots in the denominator. you would know that this is a band stop characteristic. Any questions? Okay. I'm going to move on to lecture set 6, at least talk about it a little bit. I want to at least finish out the first topic. And preview crashed. Well, there'll probably be one strictly series, strictly parallel RLC on the exam, and there'll probably be one that is not all series in parallel. So on and so on. Check bandpass characteristic. We check the number of zeros and poles. For a second order circuit, like I said, you can do that, and you can sort of gain intuition about whether or not it's bandpass based off of how it matches that transfer function. And yes, the exam is 5 problems like exam 1, just for shorter calculations. You'll have to make a determination about which transfer function you have, or you will be told which transfer function you need, AJ. Okay, so we talked about how, bandwidth is the now 4th metric we're going to look at for single transistor amplifiers. Midband gain, input resistance, output resistance could all be found using simple models. But now to find bandwidth, we must really work hard to figure it out with, more complicated models that consider finite capacitances in our circuit. And then we talked about how this looks like a bandpass characteristic. It'd be an extremely, extremely low Q bandpass characteristic. But, we have the tools to talk about, a lower cutoff frequency and a higher cutoff frequency. It's where they shift down by 3 decibels. The high pass filters for low frequency effects. So this high pass filter where the capacitor is in series with the primary load resistance, it's going to basically block the signal as frequency, blocks signal as frequency gets low, allows it through as frequency gets high. Vice versa for this low pass filter where the parallel capacitor does the opposite. We looked formally at the common source amplifier. We looked briefly at all the possible first order responses we can get for transfer functions. And then we looked at these, and then we introduced the method of short circuit time constants. So we basically say if we want to figure out the lower frequency, lower 3 dB frequency, we set our input to 0. We short circuit all the other capacitors while considering one capacitor at a time, find the equivalent resistance perceived by that capacitor. I like to do it by inspection using the equivalent T model usually, or you can use a test source and find, the ratio of your test voltage to test current. Yeah, that's what you'll do if you're a hybrid pi purist. And then you'll calculate the 3 dB frequency as this. Omega L is the sum of 1 over time constants, where the time constants is C sub k, R sub k. And now you can determine relative contributions to omega L. When we deal with the low frequency response, we will find that most of the time we're dealing with very real poles. They're extremely real. They're not even close to being complex. Though solemn, we will find that for the high frequency response, we are in danger of finding complex poles for certain amplifier configurations. I don't personally, I am not a hybrid pi or equivalent T, diehard. I will use whichever one suits my needs at the time. So, okay, here's the discrete common gate amplifier, which is a somewhat unorthodox configuration because it's got this biasing resistor pair at the gate. We normally don't do that for a common gate amplifier that already has two supplies. We would normally just tie it to ground, sometimes through this capacitor, C sub G, but this is what your book presents as a discrete common gate amplifier. So we'll have our Thevenin equivalent source V sig with R sig, coupling capacitor CC1, RS to our lower supply voltage, into the source. Out of the drain, we have our drain resistance R sub D to our positive supply voltage. And then at the drain, we connect through a coupling capacitor CC2 to our load resistance. And we're going to go a little bit long today, but strap in. So here's what the common gate amplifier looks at low frequencies. Again, we're assuming everyone's really comfortable forming small signal equivalent circuits. Whether or not that's true is up to the individual. So we leave most things the same. We replace all of our supply voltages with short circuits, usually to ground. We have no current sources to speak of, and we must leave our finitely large capacitances in because we're dealing with sufficiently low frequencies. We use the equivalent T model here because it's going to be helpful because we got stuff connected in the source of our transistor. So here's our model. So the capacitors all act independently of each other, so we can do some rapid analysis. So the circuits on the next slide help us find poles quickly. So we're going to set all sources, not just the DC ones, to 0, and analyze the circuits separately because the poles exist under 0 input conditions. So here is our input pole. So it's going to see R sig from the source, RS from the biasing network, and then also 1 over GM from 1 over GM from our equivalent T model. Since the other capacitor is replaced with a short circuit, it's like this is grounded right here. So basically, CC1 is going to perceive R sig in series with the parallel combination of RS and 1 over GM. Sure enough, that's what we have here as part of its time constant. The gate capacitor is going to see RG1 parallel RG2. Yep. And CC2 is going to see RD and RL in series. Yep. Each pole is just 1 over its time constant. So we want omega P1, this associated with this coupling capacitor right here in the source to be the dominant one, make it the largest one to achieve the minimal capacitance sum. We'll set omega P2 and omega P3 lower by a factor of less than a fifth. Ensure the dominance of omega P1 while being mindful that CG and CC2 stay small. Now you might be like, how do I possibly remember which one is the dominant pole? Well, for the 3 configurations we looked at, a fairly standard common source, common drain, and common gate amplifier, it just so happens, by coincidence, that the dominant pole is associated with the capacitor attached at the source terminal. So the source terminal capacitor is the one that we want to be dominant. It's not true 100% of the time, but generally speaking, it's usually associated with the capacitor at the source terminal, regardless of its common source, common drain, or common gate. Do we have any more questions? I'm going to call it good here. We'll talk more about high frequency models in tomorrow's lecture, and hopefully we'll move on to some examples as well. But I will see some of you in office hours. Goodbye. Bye.